Let's work these problems together about reactions in aqueous solution. The first one is an example of a precipitation reaction. We're taking barium chloride, aqueous, plus potassium sulfate, aqueous, and seeing what might react here. It's a possible partner exchange reaction. So let's look at the ions that are produced. AQ means for an ionic compound, we're going to break it apart into its constituent ions. So barium chloride becomes barium 2 plus 2 chloride ions. Then potassium sulfate becomes 2 potassium ions plus the sulfate polyatomic ion. So what we're wanting to do is see if the positive cation from one compound can react with a negative ion from the other compound. And so let's go back up to our molecular equation in that regard, now that we've seen what ions are present. So we can make barium sulfate and potassium chloride. And the question is, are either of those insoluble in solution? Well, all 1A compounds, by that I mean column 1A, the first column on the periodic table, are soluble because they contain the alkali metal ions. So potassium chloride is going to be soluble. So we're going to write that as AQ. And then we look at sulfates, and we need to look at the exceptions. And it says an exception is barium sulfate. So barium sulfate will precipitate from solution. We need to go back and balance this equation. I've got 2 chlorines on the reactant side, need a 2 in front of the KCl on the product side, and now that will be a balanced chemical equation. And so the molecular equation shows everything, even though they're ionic, as if they're complete chemical units, as if they were molecules. And so barium chloride aqueous plus potassium sulfate makes barium sulfate, this is a solid, plus potassium chloride, that's aqueous. The ionic equation shows everything as if it were broken apart in ions. So we've already done that for the reactant side. For the product side, if it's a solid, it does not dissociate into ions. So we're going to write that as a unit, a molecule, if you will, even though it's ionic. And then the AQ means that those ions are floating around in solution. So we'll write those as separate ions. We're writing the ions, yes, they are also AQ, they're aqueous, but to save space on here and be a little bit more efficient, the AQ is just going to be understood for those. The net ionic equation shows only those species that are changing form from one side to the other. And so if we look and see the potassium ion, the 2 potassium ions on both the reactants and product side, as our 2 chloride ions on both sides. So what remains is our net ionic equation. This is that barium 2 plus sulfate 2 minus reacts to make barium sulfate. This is solid. That is our net ionic equation, showing only those things that change from one side of the equation to the other, from the reactant side to the products. Those things that don't change are what we call the spectator ions. And so that's the potassium ion and the chloride ion. Those are the spectator ions. The next question asks us which of the following are strong acids, to circle those. So we have hydrofluoric acid. It's not one of the strong acids that we memorize, so it's a weak acid. Hydrobromic acid is in fact a strong acid. Nitric acid is in fact a strong acid. Sodium hydroxide is actually a strong base, so we won't circle it. And then ammonia is actually a weak base. So the only 2 strong acids out of this are HBr and HNO3. The other strong acids are hydrochloric, sulfuric, perchloric, and chloric acids, and hydroiodic acid. So those are the 7 strong acids that our book lists. The next question involves oxidation reduction, or redox. So it's asking what species is being oxidized, what species is being reduced, and to write the 2 half reactions. So let's go ahead and determine the oxidation number of everything that we see in this chemical equation. Whenever you see an element by itself, in its elemental form, its oxidation number is 0. So the solid iron and the liquid bromine, those both have oxidation numbers of 0. In the iron bromide that we see, bromine is a halogen. It's like actually going to be ionic, and so bromine is group 7. It gets a -1 charge, so it's going to have a -1 oxidation number. We've got 3 of those, and so the iron here must be +3. So this is actually iron 3 bromide. And so the iron is going from 0 to +3. That's an increase in oxidation number. It became more positive. The way you do that is by losing electrons. The loss of electrons is oxidation. So the iron is a species that's being oxidized. The bromine is going from 0 to -1. It's the gain of electrons. It's what's undergoing reduction. And so the species being reduced is the bromine. We can show this further by writing the 2 half reactions. And so we're going to take each of the 2 elements that we see. So iron, 2Fe solid, is going to 2Fe3 plus, will be the beginnings of 1 half reaction. And the other half reaction will be to take Br2 and break it apart into the ions that we see on the product side. So we see 2 Br, there's 2 out front of the FeBr3, the iron 3 bromide. So how many bromide ions do we have? We've got 6 of them. And when we're putting that, if the iron bromide is in solution, we've got an Fe3 plus and 3 bromide ions floating around. Now we got 2 times that in our balanced chemical equation, so that means we're actually going to have 6 bromides in the 2 irons. When we balance half reactions, the charge on both sides has to balance. And the only way we can do that at this juncture is by adding electrons. So in the first half reaction involving iron, it's neutral on the product side. Right now we're +6 on the, it's neutral on the reactant side, excuse me. It's neutral on the reactant side. On the product side, 2 times +3 is +6. To make that become neutral, have 0 charge, we have to add 6 electrons to the product side. The second half reaction, we've got 3 Br2 making 6 bromides. So we're neutral on the product reactant side. We've got -6 on the product side. And so to balance this, we need to add 6 electrons to the reactant side, the left-hand side. And so when we're coming up with half reactions, the electrons for both half reactions, they have to cancel one another out. So if we algebraically add these together, we've got 6 electrons on both sides. And so we would wind up with 2Fe solid plus 3 Br2, this liquid, reacts to make 2Fe3 plus 6 bromide ions, which in essence is what 2FeBr3AQ is when you show how the dissociation is taking place.